Alright, for a diffraction grating, I guess the first thing we need to do is find the separation between the lines. Now we're given the line density, right? The separation D is 1 divided by that N, where N is the line density. So it's 1 over 850 lines per millimeter. Right, so that's 850 lines per millimeter. That's let's see, that's 1.176 times 10 to the minus 3 millimeters. But I want this in MKS units. I need that in meters. So it's 1.176 times 10 to the minus 6 meters. All right? Now, for a diffraction grating, our equation is that maxima occur, well, you get light bouncing off the grating, okay, comes in normal, and it bounces off the grating with some angle theta, and it bounces off, multiple times. And the path difference, I guess, this little path difference here, d sine theta, is equal to m lambda. And this tells you where all the maxima are. Okay? So for, I guess if we want to find the angular size of the first order spectrum, we're just going to look at the difference between the 400 nanometer and the 700 nanometer reflectance. So, so let's start with lambda equals 400 nanometers. Alright, so I get 1.176 times 10 to the minus 6 sine theta. And we're in the first order, so it's 1 times 400 times 10 to the minus 9. Now if I solve this for theta, I get theta is equal to 19.9 degrees. Okay, so that's for blue light. Now for red light, I would do 1.176 times 10 to the minus 6 sine theta. And we're still in first order, but now we're doing the red wavelength. That gives me a theta of 36.5 degrees. Okay, so the difference, delta theta, which is theta red minus theta blue, gives me 16.6 degrees. So that's the angular size of the first order spectrum. Now part B wants to know what's the highest order for which the entire visible spectrum can be seen. Well, the limiting factor in terms of seeing an entire order is going to be the red light. That's got the longest wavelength, so that's going to have the biggest angle. So one way to do this would be to set d sine theta is equal to 1 times 700 nanometers and see if you can solve for theta. Then set it equal to 2 times 700 nanometers and see if you can solve for theta. And then set it equal to 3 and so on, and just keep going until you get a theta that you can't solve for. That's kind of the brute force way of doing it. I think the easier way to do it is to set theta equal to 90 degrees and find m. Right? So I would use 1.176 times 10 to the minus 6 sine 90 is equal to m times red wavelength. If I do that, I get m equals 1.68. Now the way to translate that says that m equals 2 wouldn't work, right? Because if you got m equals 2, then your theta would be impossible. So that means only one complete order is visible. We truncate that. We get about one complete order and then about 2/3 of another order. But that second order doesn't work. If you tried to set d sine theta equal to 2 times 700 nanometers, you would get theta that's impossible. So the second order is not even possible. And that's what this equation down here is telling you.